Hello and welcome back to another YouTube video, and we're gonna talk about a problem on LeetCode called validate a binary search tree. Alright, so we're given a binary search tree and we're gonna need to make sure it's a valid binary search tree. So how can we define a BST? The left subtree of a node contains only nodes with keys less than nodes, and right subtree of node contains only nodes with keys greater than the node's key, and both left and subtrees must also be a binary search tree. Right, so left child should be smaller than its parent, and the right child must be greater than its parent, and the left children must be subtree, and the right children must be binary search tree. Okay, so left and right must be binary search tree, and let's see how can we solve this problem. I made an example to illustrate how can we solve this problem. We're gonna use a recursion approach, DFS. We're gonna check the values using upper limit and lower limit, and if the value is in between those limit, which is the lowest limit possible limit and the highest possible limit, then it's a true BST. But once we find either a null, we're gonna return true. But if we found, for example, a value which isn't within the range of lowest and highest, then we know it's a false binary search tree, so we return a false result and we exit our change of recursion codes. So how can we solve this? I'm gonna remove this title, and now let's see our formula. It's gonna be value should be smaller than highest and greater than lowest. So what is the lower limit and highest limit in the root value? First element should contain lowest is infinity and highest is in infinity, so any value can work. Now to apply our recursion, we're gonna go to the left side first. We finish the left, then we go to the right side. That's how DFS and recursion could work. So now the lowest value of 6 is gonna be is gonna be negative infinity, and highest possible value of 6 is gonna be 10, because we know binary search tree must be the left child must be smaller than its parent, which is 10. So highest possible is 10, and for example 2, the highest possible value for that node at the left position is always gonna be smaller than its parent, which is 6. So our highest node gonna be 6, and the lowest is infinity, because it can be as low as long as it's below its parent value. We have 1, the next element is gonna be 1. This one is smaller than 2, which is our highest value, and lowest value is gonna be negative infinity, so it's within the range. So it's really, we have a true value right now because we have no more elements, so we return true, and we pop the back stack, we go back to 2, and we check the right side, which is 3 as the highest, but we're now moving to the right side, so now we know it's always be greater than of 2. So the lowest value should be 2, and highest value is gonna be the parent value or highest limit of the parent value, which is gonna be 6. So now we check if it within the range, which is 2 and 6. It's indeed in the range, so we return true. We pop the backstack up till 6. Now we go to the right side, we gonna visit 7. Now we're moving right direction is greater than its parent, so the lowest value is gonna be 6, and highest value should be infinity. But we need to make sure that this the right side does not exceed the parent value. So infinity really can't work here because we're within a range, and the highest possible range at that position is gonna be taken from the parent's highest value, which is gonna be 10. So the highest possible value in this case is gonna be 10, and the lowest possible value is gonna be 6. And now we check if 7 is within the range. It is. Moving on, right child is greater than 7, so the lowest is gonna be 7, and the highest is gonna be taken from its parent, which is 7. So a parent is 7, and its highest value is 10. So we're gonna take this 10 and take it as the highest value. Is 9 in between the range? It is. We return true, and we pop the back stack, and we pop that until we finish our left recursion, and we're gonna move up to the right direction, which is right direction of the root value, which is 27. Let's see, our lowest possible value is gonna be 10, since we're now at the right side of 10. So any value from 10 and to the right side is gonna be from the node of 10 to the right side is gonna be greater than 10. So our lowest element gonna be 10, and highest is infinity, since it's the first element. Now we're gonna move to the left side. We're gonna move to the left side, and this means the child is smaller than the parent, so the highest possible element is gonna be 27, and the lowest element is gonna be the highest limit of the parent, which is 10. Indeed it is, and we're gonna check the value. Is 14 in the middle? It's correct. We'll keep going to the left direction until we finish, until you find no element, or a case where it returns false if it doesn't satisfy our condition. So moving to left side, which is 11, I'm gonna check it's going left, so the highest possible value is gonna be 14, and the lowest possible value is gonna be the highest element. It's gonna be the lowest element, from its parent. So it's gonna be 10 and 14 for the highest. And we're gonna check the value. Is 11 in between? It is. We return true. We pop the back stack and move to the right direction. Here we have 20. Let's see. We're gonna 20 is greater than the right child is greater than its parent. So now we're gonna check we need to identify the lowest and highest. So the lowest element is gonna be 14, because we know the right child is always greater than 14. So the lowest the lowest limit is gonna be 14, and the highest limit is gonna be taken from its parent, which is 27. Indeed, check the value. 20 is in between, correct. Return true, pop the back stack. We're now at 27. Now we're gonna finish the left side. Now we're gonna take the right side. We have 30. 30 is greater than 27, and so the lowest limit possible for the right side of 27 is 27, and the highest possible one is infinity. Alright, we check 30 is in between, indeed. And then moving on, the same algorithm goes on, and we're comparing it. Last element, it's indeed in between the range, which is the lowest of 30, which is the parent's value, and the highest of the parent's highest value. And indeed it is true. And that's it for the algorithm. So we need to make sure we calculate the time complexity and space complexity of this problem. Now we pop the final stack, which is, now we have finished our algorithm, and we pop the stack, and it's all done. Now we need to calculate the time complexity and space complexity. Speaking of time complexity, we're checking a two comparison every time we check a node. So basically we're making two operations for every element, so basically it's 2n. So now we compare it, the operations is comparison, we're comparing it with the lowest and highest. So there are two operations which we really don't compare about constant value, which is 2, so basically it's O of n. And for space complexity we will have O of h, and h is the height of the tree, because we're using recursion, and recursion keeps reference to the backstack, and backstack at most would be from the root value up till the leaf, which is which is considered as the height. So the maximum possible height here, for example, is 10, 6, 2, 1 up to the maximum possible height for this tree is our space complexity. Since once we reach the maximum height, we pop the stack and we go backward. We check if it's right, if there is possible right or not, and moving on. So the highest, at worst case, we will have O of h, and if there is a condition for if we met, for example, a condition, if it's not 14, it's for example like 29 or whatsoever, and it doesn't match our condition, so we return false, and then it's gonna be less than h. But at normal case it's gonna be O of h. If we're gonna at worst case, I mean, it's gonna be O of h. So that's it for our algorithm. So I think that's it for our algorithm, and those are time complexity and space complexity. And let's get